Welcome to section 1.5, linear functions, equations, and graphs. The initial definition for this section is on page 29, definition 1.13. A linear function is any that can be written in this form: f of x equals ax plus b, where a and b are any real numbers. So that definition basically means that anytime we see something that looks like this, it's going to be a line. Now we saw lines before. We saw lines in the form y equals mx plus b. So we can equate these two ideas. Remember, y and f of x are essentially saying the same thing. They're telling you what the outputs are. And our input value is going to be x. So this is a function of x. We see the correlation between the coefficient of the x value, or the x variable, and the correlation, in fact, we ended up actually using the same letters for these, between the constant, between the piece of the equation that doesn't involve a variable of any kind, the constant term. So, if we have a linear function in this form, in the standard form, we can graph it very quickly. Using that same procedure, we can plot the y-intercept and then use the slope to find other points, ultimately giving us the graph of our line. So really quickly, I would just like to confirm that f of x equals 3x minus 7 is a linear function. Well, we don't need to do too much work here. This function is in exactly the same form as this first definition in this section. So here we have our slope, and here we have our y-coordinate of the y-intercept, b. So we could graph this if we wanted to, but at the moment I will just say that this is a linear function. So our next task will be to actually graph this function. So I will set up my xy plane. Now since we're not calling this dependent variable y, since we've named the function f of x, I could say that the vertical axis is the f axis, if we wanted to. You could call it y, doesn't matter which one. Alright, so what do we know about this graph? Well, we know our y-intercept is going to be at a height of -7, so if I plot 1, 2, 3, 4, 5, 6, 7, that will be my y-intercept, or my vertical intercept. And I see that we have a slope of 3. So if I rise 3 units and I run 1 unit, I can find another point. If I rise another 3 units and run 1 more unit, I can find another point. My tick marks are a little uneven, so this might not look exactly like a line. But we see the same behavior if we rise 3 more and run 1 more. Or, if we wanted to, we could fall 3 and run in the negative direction, find another point. Connect all of those up, and like I said, this is going to be a little bit wiggly, but that is what a ruler would help me solve. So that is our line. This would be f of x equals 3x minus 7. Now, if this function represented actual physical quantities, or even less concrete quantities, such as money, we could identify the rate of change as being 3. Our slope. So what that tells me is that for every increase of 1 unit in the horizontal direction, our graph will rise 3 units. So the rate of change, if we were talking about money over time, we might say with every additional day or week or whatever our X value represents, our dollar amount increases by 3. So that is how we would use the rate of change. The other important topic in this section is that of the point-slope form. So we have seen slope-intercept form before, and that is very useful in terms of relating the slope and the y-intercept. However, we don't always necessarily know what the y-intercept of a line is. In this case, my graph is not the most amazing picture, but you can kind of tell that the y-intercept isn't quite at 1. Now, generally we don't want to guess about the y-intercept. If it doesn't look like it definitely passes through a certain point, we can't really use it. But we have 3 other points that we could use to come up with an equation for this line. So those points that we have the point 1, 1, we have the point 4, 0, and we have another point off to the left at negative 2, 2. So, what do I need to do with these? Well, I have 2 forms of linear equations. I have the slope-intercept form, and I have what we call point-slope form. So slope-intercept form is usable when we know the y-intercept. Point-slope form is usable when we don't. So we need the slope in either case, but in point-slope form, the only other thing that we need is one other point. So what I need to do first is calculate the slope. And since I have the graph, I can use the rise over run method. I could go from the middle point here at 1, 1. If I rise 1 and I run 3 in the negative direction, so if I rise 1 and I run negative 3, that would give me my slope. We're looking at a slope of negative 1/3. Now I can use that point slope form. There are a couple of different versions of it. I quite like the first version that's given in the notes under definition 14 in this section, but we might skip ahead and use that secondary definition, y equals m times x minus x1 plus y1. Now we already know the slope. We know the slope is negative 1/3, so we can replace the m with its actual value. But the definition says that we are going to replace x1 and y1 with the x and y coordinates of one of our points. So I think I'll go for the middle point, since it's kind of nice. I can do x minus 1 plus 1. So there's our x coordinate and our y coordinate, replacing the placeholders. Okay. So to put this into slope-intercept form, I need to write it in that form y equals mx plus b. So right now it's a little jumbled. If I distribute negative 1/3 across the parentheses, I'll get negative 1/3 x plus 1/3 plus 1. And finally I can combine like terms. 1/3 plus 1 will be our constant, and 1/3 plus 1, another way to write 1 would be 3/3, would give me 4/3. So that is our slope-intercept form. Now, we chose this point 1, 1. What would have happened if we had chosen another point? Well, we could do the same type of thing. We could say y equals the slope, m, negative 1/3, times x minus, I think I'll try this point. We're going to substitute in the x value, 4, and the y value, which is 0. That's actually kind of nice. If you can use a point that has one coordinate as 0, that makes your life a little bit easier. So the only thing I need to do now is distribute the negative 1/3, so negative 1/3 x. Negative 1/3 times negative 4 would give me positive 4/3. And we end up in exactly the same place. So this version was a little bit shorter because we did have that y coordinate of 0. But we should always end up with the same equation because we're trying to describe the same line in either circumstance. This line passes through both of these points. In fact, if we had used our third point, our solving process would have looked a little bit different, but we should have ended up in exactly the same final form of the equation. Now, another topic in this section deals with how to describe a horizontal or a vertical line using an equation. Now, a horizontal line, as discussed in a previous section, has a slope of 0. So one approach that we could use is to use point and slope form. So we could say y equals m times x minus x1, in this case 4, plus y1, so plus negative 1. Now, one of our properties of the real numbers says that anything times 0 is 0. So this piece completely disappears, and we just get y equals negative 1 as the equation of our line. Now this kind of makes sense. Another way of viewing this is y equals mx plus b, where m is, again, 0, so this piece disappears, and b is, in fact, our y-intercept. Now that kind of makes sense because a horizontal line passing through 4, negative 1 is also going to pass through 0, negative 1. I'll show you what I mean by that. So 1, 2, 3, 4, negative 1. If we create the horizontal line described in this problem, we will see that it ends up intersecting the y-axis at a height of negative 1. In fact, every coordinate, or every y-coordinate on this line is negative 1, regardless of what the x-coordinate is. So that's how we would find the horizontal line. It's going to be y equals whatever the y-coordinate of the point which we have to use is. On the other hand, a vertical line does exactly the opposite. So the graph of this, again, this line is going to pass through the point 4, negative 1, but this time it will be vertical. Now, none of our equations admit a vertical line. This has undefined slope. In fact, this is, if we go back to the previous section, if we apply the vertical line test to this line, it's not actually a function. So our function form, f of x equals ax plus b, isn't going to help us here. But what we can observe is that every single point on this line has an x-coordinate of 4. They all lie along that vertical line, regardless of what the y-coordinate is. If we were interested in describing every single point on this line, we could say that x equals 4 and say nothing about y and be done with it. So that is how you describe a vertical line. It's going to be x equals whatever the x-coordinate of your given point is. The next topic in this section is that of lines which are either parallel or perpendicular to each other. So that definition is definition 1.15. So our first bullet point there says that if two lines have the same slope, if their slopes are equal, then they are parallel. Our second definition says that if the slopes multiply to -1, in other words, if they are negative reciprocals of each other, then they are perpendicular. So, we are going to use those definitions to come up with equations for lines parallel and perpendicular to lines that are already given. So in this scenario, we want to find the equation of a line that is first parallel to a given line, f of x equals 3x minus 1. And we want that line that we find to pass through the point 0, 6. So, to come up with an equation for a line, we always need two things. We need the slope and a point. We have the point given to us, so the only question is, what should the slope of our line be? Well, since we would like to be parallel to this line, we would like it to have the same slope. Now, the slope of this line is going to be 3, since that is the coefficient of x. So if we put those two together, we can either use point-slope form, or in this case we're very lucky because the point that we would like to pass through is on the y-axis. So we could consider this to be our y-intercept, 0, 6. So I think it's going to be a little bit easier for us to use slope-intercept form. I can say the equation is going to be y equals 3x plus 6. So here we've inserted our slope and our b, the y-coordinate of the y-intercept. Alright. So we could leave it in that form, or we could write it in function notation. We could say f of x equals 3x plus 6. Now we could have gotten to this result using the point-slope form as well. We could say y equals m x minus our x-coordinate 0 plus our y-coordinate 6. And we see that that 0 isn't contributing much, so it disappears, and we get f of x equals 3x plus 6, just the same. Now for our second part, we would like to do something similar. We would like to find a line passing through the same point, but this time we would like it to be perpendicular to the line that we base everything off of. Okay, so I'll use that definition, the second bullet point in definition 15, to say that the slope of the line we are going to come up with should be the negative reciprocal of the current slope. So it should be -1 over the current slope. And we are still passing through the same point, 0, 6. So again, you can use point-slope form. Point-slope form, it's worth noting, will always work as long as you have any point plus the slope. Slope-intercept form, while it is more concise and nicer to work with, is restricted in that you can only apply it when you have the y-intercept. In this case we do, so I will default to using that one. So I'll say y equals m x plus b. Now if you plot both of these functions that we came up with, we could rewrite this as f of x equals -1/3 x plus 6. So if you plot, not that one, if you plot any of these lines that we came up with and the line that we were basing them off of, you can visualize how the lines we came up with and the original are either parallel or perpendicular. So I'll do that now. I'll go into my y equals screen and I'll type in the equation of each of these lines. I'll type our starting line to begin with, 3x minus 1. And we'll graph that just to see what we're basing everything off of. And adjust your window as necessary. I think a standard zoom should work here. So standard zoom, if you go to the zoom menu and come down to standard, this will get you back to that default 10 by 10 by 10 by 10 with tick marks every unit if you've got something strange going on with your window. In fact, if your calculator is behaving oddly, if you're trying to graph and nothing is appearing or you're getting an error, try resetting to the standard zoom. It usually fixes most problems. So if we go back and plug in both of the other lines that we came up with, the parallel line and the perpendicular line, both passing through 0, 6, we'll get a chance to see exactly how all of these look in comparison to each other. So we've got our parallel line here, and it is in fact parallel to the line that we started with, and it does pass through the y-coordinate that we are interested in, 0, 6. And here we see the perpendicular line, and it also passes through 0, 6. Now, with the window as it is, it may not look exactly perpendicular. It doesn't look like exactly a right angle between this line and the one that it was based off of. The reason for that is that your screen is a little bit wider than it is tall. So if you're fitting 10 tick marks, or 20 tick marks rather, into a wider space, horizontally than vertically, it's going to stretch it out and distort the window a little bit. So to remedy that, to see that these really are perpendicular to each other, you can go into the zoom menu and choose a square zoom. So that will take whatever window you currently have and just adjust it a little bit so that your tick marks are proportional in both directions. So if we do that, we can see that those definitely look like they are perpendicular to each other. So the final question I'd like to ask out of this section is, how do we know if two lines are perpendicular or parallel to each other? Well, we can apply the definition in a slightly different way. So here we have two lines, y equals 5x minus 1 and y equals 1/5 x plus 3. And I would like to know if they are perpendicular. One option would be to graph both of them, and we'll do that at the end. But we could also think about what it means for two lines to be perpendicular. Remember, in our definition, the slopes have to multiply to -1 in the case when lines are perpendicular. So we see our first line has a slope of 5. We see our second line has a slope of 1/5. If we multiply those together, we get 1. We don't get -1. So these are not perpendicular to each other. Moreover, they are not parallel to each other since the slopes are not the same number. So these lines are neither parallel nor perpendicular, and to confirm, I'll throw those both into the calculator with that square zoom and see that indeed they are not even close to either option. So if I go to the y equals screen, I'll clear out the old functions that were in there, and I'll enter our first line, 5x minus 1, our second line, 1/5 x plus 3, and we'll graph, and again our window is satisfactory to see both of these. If it's not, you can always try a fit zoom, but these definitely don't appear to be either parallel or perpendicular. So those are special cases. Lines are parallel and perpendicular very infrequently. Most of the time they're just going to be minding their own business, existing in the xy plane, and they're not going to have any particularly impressive relationship to one another. So that is all for 1.5. Check back for the next chapter, and be sure to get started on those homework problems.